In our last video, we demonstrated the phenomenon called beat frequency, when two different audio tones that are nearly identical are played together like this. That's what it sounds like when the two tones are very close in frequency to each other. The pulsing we hear is the beat frequency, which is simply the mathematical difference between the frequencies of the two tones. But is there a beat frequency when the two tones are so far apart we can't hear any pulsing? The website we're using for this experiment is onlinetonegenerator.com. Let's set our tone generator on the left at 4,000 Hertz, and on the right 4,440 Hertz. The difference between these two tones is exactly 440 cycles per second, which on the musical scale is A above middle C. So if we play them at the same time, we should be able to hear that note. Well, theoretically it's there, but I didn't hear it. If it is there, the two tones that we're playing to produce it may be drowning it out. Is there some way that we can mix these two tones together and then filter them out so that we are left with only the beat frequency between them? To do this, we need to build a circuit called a balanced mixer. It consists of 4 diodes, all connected in a ring, all allowing current to flow same direction within the ring. The 2 transformers with a center tap in the secondary winding give us the output signal, the beat frequency, without the source tone that produces the beat frequency. You'll find a link to the schematic diagram in the description below this video. Now this looks a lot like the diode bridge we built for an earlier experiment when we converted alternating current into direct current. But if you examine these two circuits closely, you can see that they are not the same. You may want to pause this video and carefully examine the orientation of each diode within these two circuits to see what I mean. Okay, so let's build this balanced mixer with our trusty snap circuits. The completed balanced mixer looks like this. Snap circuit aficionados may notice that we have taken to building our own components with pieces of plexiglass and pop rivets. For this experiment, we are using 2 separate computers for our tone sources. And connect the audio output of each computer from the earphone jack to the input lines of the mixer. We'll simply connect the output of the mixer to a computer amplifier and speaker. We set the tone generator on one computer to 4,000 Hertz and 4,440 on the other computer. Let's fire up the tone generators and hear what comes out the other end. This is the beat frequency between 4,000 Hertz and 4,440 Hertz. Let's check it with the piano. 440 Hertz is A above middle C. How cool is that? Actually, what comes out of the balanced mixer is not just the tone that is the difference between the two original tones, but also the sum of the original tones. In this case, the sum of the two tones is nearly 8.5 kilohertz, which is the upper limit of my range of hearing, although my grandkids can hear it. We can demonstrate that upper beat frequency this way. Let's start again at 440 Hertz, that note we call A above middle C, and let's reduce it by 10 cycles per second. Then on the other computer, increase that 440 by 10 cycles per second. The difference between them is 20 cycles per second, so we can expect that to be the beat frequency. If we play these two tones together without the mixer, it sounds like this. We hear a rapid pulse, which is the 20 Hertz beat frequency. But listen to what happens when we feed the 430 and the 450 Hertz tones from separate computers into our balanced mixer. What's that note? It's the sum of the frequencies of the two source tones. 430 plus 450 is 880 Hertz, and we know that as A above high C on the keyboard. And it is. The 20 Hertz beat frequency is also there, but the pitch is too low and the computer speakers are too small for us to be able to hear it. However, for our demonstration here, for the purpose of learning how a metal detector works, we are primarily interested in the lower beat frequency, that is, the difference between the two source tones. Now there's one more experiment that we need to do with our balanced mixer. We set the tone on one computer at 10 kilohertz. That's 10,000 cycles per second. And on the other computer, we used the sweep generator function that the website offers us. This generates a tone that gradually increases in frequency, like this. What happens when we feed both the stationary tone and the sweep tone into our balanced mixer? The mixer should cancel out both tones and give us only the beat frequency between them, like this. As the frequency of the sliding tone approaches the stationary tone, the difference in frequency between them decreases, and so the pitch of the beat frequency drops. Then as the sliding tone continues to climb away from the stationary tone, the difference between them increases, and the pitch of the beat frequency rises. Let's hear that again. Now let's reset the sweep generator so that the pitch drops over time like this. Whether the sweep generator tone climbs or drops, the effect is exactly the same. So what does all this have to do with understanding how a metal detector works? That will become evident as we take the first step to actually building the circuit.